Good afternoon, everyone. Today I will present my research on imputing knowledge tracing data with subject-based training via LSTM variational autoencoders. My research is motivated by three factors. One, in today's deep learning field, models are becoming bigger and more complex, craving for more data to achieve the expected results. Two, in the KT field, it has been a long issue to have missing data which has been limiting the deep learning models to perform well. Three, to generate the KT data is hard because it is a longitudinal data which not only compresses time-varying features, but also the time-invariant subject descriptors. Therefore, our work proposes to solve this issue using deep generative models, specifically LSTM variational autoencoder and LSTM longitudinal variational autoencoders with subject-based training. To set up the problem, we let y be the time-varying samples and x be the subject descriptors, NP as total samples for student T, Z being the latent space. Then the time-varying samples for student P can be expressed as yp, a set of y1 to ynp with t time steps. Subject descriptors can be represented by xp, a set of x1 to xnp for t time steps with q dimensions. To generate data, first we parameterize the adjoint generative model Pw of y and z equals p psi of y given z times p theta of z. To find z given y, VA uses an approximate posterior distribution of q phi of z given y and fit the problem by maximizing the elbow, which is the evidence lower bound, via the following equation, of which EQ of log P psi of y given z is the reconstruction error that measures the difference between the input and encoded decode data, and DKL is the Kalbach-Leibler divergence, used to measure the distance between the approximate and the true distribution of z. In practice, we minimize the negative elbow as a loss function to trace. We create LSTM kernels for both VAE and LVAE frameworks, and for simplicity, we call them VAE and LVAE. From the left figure, we see both frameworks first project the data into latent space Z in the encoder block, and then decode original data from the latent space via elbow loss training. LVAE differentiates from VAE in two areas. First, VAE assigns equal weight to the reconstruction error and the KLD, while LVA assigns a weighted KLD to the final loss. Second, LVA trains an additive Gaussian prior model to extract the relationship between the subject descriptor X and the latent space Z. Moreover, our work takes a subject-based training strategy where we split and impute data by student IDs instead of roll number. We call the roll number splitting as non-subject-based training. From the figures below, we see the data parts split by IDs versus by rows are different segments. The benefit of splitting by IDs is to keep the complete sequence of each student before and after imputing. Here's a summary of our framework that includes 4 phases: input phase, generative phase, predictive phase, and retraining phase. We now go through some details of our experiments. In the step of data processing, we use 2 private data sets from K12.com, with the first data from the grade 10 geometry course and the second one from the grade 11 algebra 2 course. The data set contains 11 time-varying features and 7 subject descriptors. We use different split ratios for generation and prediction and apply both ratios to subject and non-subject-based training. All the data are aligned for a specified fixed sequence length S. If a sequence is longer than S, it will be cut short, while the shorter sequence will be padded. We apply 3 padding strategies to find the optimal performance: zero padding, F-fill, and B-fill. F-fill means pass forward with the last value V, while B-fill pass backward with the first value W. Further, we identify all the missing data by comparing to students to the school quiz-taking schedule. After data processing, we generate data via 3 generative models: VAE non-subject, VAE subject, and LVAE subject. After data is generated, we impute them back to the same students by by IDs, and hence the imputed data gets longer sequences. To predict the downstream KT data, we train 3 predictive models, LSTM, ADA-RNN, and Transformer, by different padding strategies to find the best performance. After that, we use the best predictive model to predict the target variable for the generated data, which will then be imputed back for reprediction. Here we shared some details evaluating results of the experiment. First, we evaluate the quality of data generation by comparing the feature distribution between the original and the generated data. As shown in the figure below, the data generated from VAE-NS were far from the original data, and the generated data from VAE and LVAE are both quite close to the original data, with LVAE being slightly better. Next, we evaluate the effectiveness of the imputed data. First, we use the best performance from table 2 in boldface to predict the target variable for the generated data and then impute them back for reprediction. Table 3 showcases the average repredict performance over 10 random seeds. We can tell that adding the generated data from VAE and LVAE makes RMSE drop about 50%, while the one from VAE-NS not much so. This clearly indicates superior boosting capability from the subject-based generated data. Furthermore, we evaluate the robustness of the imputed data. We find that it only needs 10% of data to exceed the original model performance for LSTM and ADA-RNN, while it needs about 50% to boost the original performance for the transformer model. To sum up, we generated good quality data from VAE and LVAE frameworks with subject-based training, which surpassed the original models by about 50% in average RMC. Second, through the validation on the robustness of the imputed data, we discovered that it only needs 10% of imputed data to boost predictive performance for small to medium models. As future steps, we might process data into varying lengths instead of fixed lengths to test the effectiveness of the generated models. Thank you so much for your attention. Any questions?